Welcome back. We were looking at properties of vector space. Okay. So, first of all, vector addition is commutative. We just saw the proof of this. Next, we saw vector addition is associative. We completed the proof of this. Now, let's look for the next property, existence of additive identity. The zero vector, that is 0, 0 in two-dimensional R space, is the additive identity. What does additive identity mean? Let U, vector U, be U1, U2, any vector. Then U plus the 0 vector, U1 plus 0, U2 plus 0, is back to U. Likewise, 0 vector plus U is 0 plus U1, 0 plus U2 is back to U. That's what it means to be additive identity. It doesn't change the identity of any other vectors upon addition. U plus 0 vector is 0 vector plus U is U. Likewise, in three-dimensional vector space, 0 vector is 0, 0, 0. It is the additive identity. Let U be any vector in R3, U1, U2, U3. Then U plus 0 vector is U1, U2, U3 plus 0, 0, 0. Turns out you get U back. Likewise, 0 plus vector U, 0, 0, 0 plus U1, U2, U3, you get U back. That is, U, vector U plus the 0 vector is U. 0 vector plus U is U. So, three properties. Addition is commutative, addition is associative. We saw that there exists an additive identity. Now, existence of additive inverse for any vector. Let U be any vector in R2 or R3. Let's show the existence of vector V such that U plus V is the 0 vector. Well, if vector U is U1, U2, let V be negative U1, negative U2. Likewise, in R3, if vector U is U1, U2, U3, let V be the vector negative U1, negative U2, and negative U3. In either case, vector U plus vector V is the 0 vector. Such a vector V is called inverse of vector U. Okay, so four properties of addition. Addition is commutative, addition is associative, there exists an additive identity, and then you can show the existence of additive inverse for every vector. Now let's look at properties of scalar multiplication. Scalar multiplication is distributive over vector addition. Let C be any scalar, U, V be any two vectors either in R2 or R3, fix one size. Then scalar multiplication splits over addition. C of U plus V is CU plus CV. Let U be U1, U2, V be V1, V2. Then C times U plus V is C times U1, U2 plus V1, V2. Notice it's in parentheses, so you add them first. How do you multiply C? Well, it goes component wise. C times U1 plus U2, C times U2 plus V2. Now notice multiplication among real numbers is distributive over addition. So C distributes to U1, V1, C distributes to U2, V2. This vector can be split CU1, CU2, CV1, CV2. That is C times, so that's the scalar multiplication of C with vector U plus scalar multiplication of C with vector V. Is the same story when you are dealing with 3 space. Multiplying by C to the sum of U plus V means you add U and V first. You add these two, then multiply by C. C goes component-wise. C distributes over each one of these because these are now real numbers. C, multiplication over reals, is distributive over addition. So it splits. Then finally this vector splits into sum of two vectors, and then you can get the scalar out in each case. So C times U plus V is Cu plus Cv. So what did we say about multiplication? First, it is distributive over vector addition. Now this is the second property. Scalar multiplication is distributive over scalar addition. What does that mean? You have two scalars, C and D, and one vector U. I hope you see the difference. In the previous case, over scalar multiplication is distributive over vector addition, so you have two vectors and one scalar. Now you're talking about multiplication being distributive over scalar addition, so you have two scalars and one vector. Add the two scalars first and then multiply to the vector. You should get distribution C times U and D times U. So let's prove this. Let U equals vector U1, U2, then C plus D times U, that's one scalar. It multiplies to each component, U1 and U2. Now here is multiplication among real numbers. This is real number multiplication. Real number multiplication is distributive over real number addition. So you have distribution. Once you distribute, you can split this vector into two vectors. Once you split them into two vectors, you can get the scalars out and you have the result you want. Okay? So, two scalars and one vector multiplication is distributive. Same story in three-dimensional space. You have two scalars, one vector. Add the two scalars, scalar multiply to the vector component wise. Now here is real multiplication, which is distributive over addition. You get these. Now you are able to split the vector into two, get the scalars out, and you have the result you want. What about associative? Scalar multiplication is associative, but you need two scalars. We don't know to multiply two vectors. You need two scalars. Let CD be two real numbers and U be any vector. I multiply the two scalars first and then multiply to the vector. Or I multiply the scalar one at a time. Either way, the result is the same. That's what this means. This is scalar associativity of scalar multiplication when you have two scalars. Let's prove this. Let U be the vector U1, U2 in two-dimensional space. CD times U. Well, CD will go to each component. Now, multiplication among real numbers is associative. So the parentheses can be moved over, which means this scalar can jump out. This scalar jumped out, and look at that. You can get the next scalar out, hence the parentheses. So this vector alone is D times this vector. So C outside, D inside with the vector U, and that is associativity of scalar multiplication. Similar story when you're looking at three-dimensional. There is a typo here. It should be CD U3, just as you have CD U1, CD U2. It should be CD U3. C, the multiplication among real numbers is associative, so the parenthesis is moved, thereby getting the C out. Then you get the D out within parentheses, and that is your multiplication associativity. What about scalar multiplicative identity? Multiplicative identity, for any vector u, 1 times u is itself. Let u be the vector u1, u2. 1 times u is 1 times u1, u2, which is 1 times u1, 1 times u2, which is u1, which is u2. So that's u. Similarly, in 3-dimensional, 1 times u is 1 times u1, u2, u3, 1 times u1, 1 times u2, 1 times u3, which in turn is u1, u2, u3, u. Okay? So this gives us the following theorem. U, V, W vectors in 2-dimension or 3-dimension. CD real numbers, then the following properties hold. Addition, vector addition is commutative. Vector addition is associative. There exists a zero vector, that is the additive identity. For every vector u, it has an additive inverse. What does the additive inverse do? U plus negative u is the zero vector. Okay, and notice addition is commutative, so you can flip this around. What about scalar multiplication? So the first 4 properties are only about addition. Now next 4 properties will be about how multiplication interacts with addition. Multiplication, not any multiplication, scalar multiplication distributes over vector addition. Scalar multiplication distributes over scalar addition. Scalar multiplication is associative. I have 2 scalars. I multiply the scalars first, multiply to the vector, or I multiply the scalar one at a time. Answer is the same. Lastly, scalar multiplication has a multiplicative identity. 1 times a vector is the vector. Okay, these are the important 8 properties of which define vector space. First 4 properties are all about addition. Next 4 is about scalar multiplication and how they interact with vector addition. Which completes our section 4.1. Here are the homework problems. Okay, have fun.